We're at 13.5b, and we're going to talk about inclusive events in probability. We have one previous video to this lesson, 13.5a, and it's linked in the description with the geometry playlist if you need it. A simple event is an event that describes a single outcome. It'd be like rolling a number cube and the event consisting of the outcome 3. Getting a 3, that's a single outcome. That's a simple event of rolling the number cube. A compound event is an event that is made up of two or more simple events. So it would be like tossing a coin and rolling a number cube, the event of heads and rolling a 3. So the coin would have heads and the cube would have a 3. That's a compound event. Mutually exclusive events are events that cannot both occur in the same trial of an experiment. So that would be like rolling a 3 and a 5 on a number cube. We can't have both, so they're mutually exclusive events. Inclusive events are events that have one or more outcomes in common. When we roll a number cube, the outcomes rolling an even number and rolling a prime number are not mutually exclusive. They could happen at the same time. So if we have even numbers of 2, 4, and 6, and we have prime numbers that are 2, 3, and 5, the number 2 here is both prime and even. So the events are inclusive. This is our Venn diagram. So there are 3 ways to roll an even number: a 2, a 4, and a 6. And there are 3 ways to roll a prime number: a 2, a 3, and a 5. So even and prime is 2. This symbol is an intersection, and it means and. The outcome 2 is counted twice when the outcomes are added, 3 plus 3. The actual ways to roll an even number or a prime number is 3 plus 3 minus 1, which equals 5. And the concept of subtracting the outcomes that are counted twice brings us to the probability formula for inclusive events. Now, if you're very confused, stick with me. Hopefully by the end of the video, you'll totally get it, okay? So, for your notes for inclusive events, the probability of 2 inclusive events, A or B, occurring is the sum of their individual probabilities minus the probability of both occurring. So in algebra, it would be for 2 inclusive events, A and B, we'd have the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Here's an example. When we roll a number cube, the probability of even number or prime number is equal to the probability of even or prime, which is equal to the probability of even plus the probability of prime minus that probability of even and prime. So even numbers, we had 3 out of 6. The 2, 4, and the 6 were the even numbers. And the prime numbers were 2, 3, and 5. We subtract 1/6, and it's going to equal 5/6. Stick with me. We'll explain this. We can find the probability of an inclusive event, such as rolling a 5, or an odd number on a die, on a number cube. So on a number cube, there's 1, 5, and there's a 1, 3, and 5. Those 3 numbers, those 3 faces would be the odd numbers, wouldn't they? So rolling a 5 or an odd number on a die, on a number cube, would be the probability of 5 or odd, and it's going to equal the probability of getting the 5 plus the probability of getting the odd. So we're going to have 1/6, because there's only 1 out of 6 faces that's a 5, plus 3/6, because there's 3 out of 6 faces that are odd, and we're going to subtract the probability of 5 and odd. That's going to be 1/6. For it to be a 5 and an odd, it can only be the 5. That's 1 out of 6 faces on the number cube, so that's a 1/6. So 1/6 plus 3/6 is 4/6. We subtract that 1/6 again. I'm going to have 3/6. You can also look at it as canceling this 1/6 and this one as inverses, can't we? We end up with 1/2 when we reduce it. What is the probability of rolling at least 1 4 when rolling 2 dice? Well, this has 6 faces and this has 6 faces. And if we roll both dice, we need to get at least 1 4. So that means we could roll a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, and we could keep going. So the probability of 4 or 4 would equal the probability of 4, which would be one side out of the 6 faces, so that's 1/6, plus the probability of this one landing on a 4, which would be 1/6, minus the probability of a 4 and 4. That would be 1 out of 36, or 1/36, because there's one outcome of 36 where both dice would show a 4. So we do common denominators, right, to do the subtraction. So we can turn this into 6/36 and this into 6/36. And we subtract the 1/36 and we get 11/36. That would be the probability of rolling at least 1 4 when rolling 2 dice. By the time we listed all the possible combinations of how they could land, we would have 36 of them, okay? It landing on 1 and then all of these 6. This one landing on 2 and then all of these 6. Landing on 3, all of these 6, so on, okay? So we would just do 6 times 6 to get 36 quickly for the possible combinations. If the combinations thing really confuses you, then you missed video 13.1c, and there'll be a link to that in the description so you can review it very quickly before moving on. Now, if you remember back from grade school or middle school, a Venn diagram is a diagram that shows the relationships between sets. And we can make and use a Venn diagram to help us find the probability of inclusive events. Of 3,510 people surveyed, 1,950 were male, and 103 were colorblind. Only 6 of these colorblind people were female. So what is the probability that a person was male or was colorblind? Very important, the word or. We make our Venn diagram with the data given here. And being male and being colorblind are inclusive events. So everything inside this rectangle represents all 3,510 people surveyed. We have 1,950 that were male, and we had 103 that were colorblind. 6 were female, so 103 minus 6 would be 97. So the 97 would go right in the middle, right here. And 1950 of the males minus this 97 gives us 1,853. We find the number in the overlapping region. This 103 minus 6 is 97, so that's 97 colorblind males. We removed those 6 females. Now we find the probability that a person was male or was colorblind. The probability of male or colorblind is equal to the probability of being male plus the probability of being colorblind minus the probability of being male and colorblind. So we had 1,950 males. The total was 3,510. So we do this number on top of this number. Then we add the 103 colorblind people on top of the total of 3,510. And we subtract this number, 97, for the colorblind males divided by the total of 3,510. We do our math, get our calculator, and we find out we have 1,956 over 3,510, We do the division, we get this nice long decimal, which is approximately 0.557, or it's about 55.7%. And that would be the percent of male or colorblind. So Venn diagrams can help you. You just got to make sure you put the information in correctly. We've learned that the complement of an event with probability P, which are all the outcomes that are not in the event, has a probability of 1 minus P. We can use the complement to find the probability of a compound event. And there are 5 people in a movie club. Each person randomly chooses a movie from a list of 10. So what's the probability that at least 2 people in the club choose the same movie? So at least is really important. The words at least tell us to use the complement. So if you see that, that's a clue. You know it's a hint to use the complement. And the probability at least 2 people choose the same movie is going to equal 1, or 100%, minus the probability that all choose different movies. The probability that all choose different movies is going to be the number of ways 5 people can choose different movies divided by the number of ways 5 people can choose movies. So we would do the number of permutations of 10 objects taken 5 at a time divided by 10 to the 5th power. And that's going to equal 10 times 9 times 8 times 7 times 6. We did this earlier in the chapter. If you missed it, there's going to be links in the description. And that's going to be over 10 times 10 times 10 times 10 times 10. That's going to give us 30,240 over 100,000. We do our division and get 0.3024. So the probability of at least 2 people choose the same movie is going to equal 1, that's like 100%, minus the 0.3024. That's going to give us 0.6976, or we can write it as a percentage as 69.76%. So the probability that 2 people choose the same movie, it's about 69.76%. It's close to 70%. So, if you missed this lesson and this is confusing you, just click in the description and go back to 13.1a and 13.1b and start watching from there, and you'll pick up anything that you might have missed. Now be careful when working with inclusive events and mutually exclusive events. You might double count a probability if you treat an inclusive event as a mutually exclusive event. If a total probability is greater than 1, you know you made this error. We ask ourselves whether the events can occur simultaneously or not before we choose the form of addition rule to use. Mutually exclusive events, they can't occur simultaneously. We covered that in the last video, 13.5a. We would have the probability of A or B, and it would equal the probability of A plus the probability of B. For inclusive events, the probability of A or B would equal this probability of A plus the probability of B minus the probability of A and B. They can occur at the same time. Remember our symbols? This means or, and this means and. Okay? So I want you to remember that there's no harm or shame in not understanding a math concept. There's no harm or shame in rewatching a video to completely understand, or going back to watch previous ones that you might have missed. I hope you have a great day, and I'll see you next time. Bye.